Right now, every spacecraft humanity has ever built was designed to last years, maybe decades. The longest functioning probe in history, Voyager 1, has survived 47 years and is already failing. Now imagine building a spacecraft that must function flawlessly not for decades but for centuries. Thousands of people living, breeding, dying inside a sealed metal world, hurtling through interstellar vacuum with no possibility of rescue, resupply, or return. Engineers have studied this problem seriously, and the answers are terrifying. The barriers are not what science fiction taught you. They are not dramatic explosions or alien encounters. They are silent, invisible, and cumulative. Entropy, radiation, genetic drift, ecological collapse, and the slow degradation of every material ever manufactured by human hands. This is the true science of generation ships, and it changes everything you thought you knew about interstellar travel. If you enjoy deep explorations of real science that challenge how you think about humanity's future, I genuinely appreciate it if you hit that like button and subscribe. It helps more than you know, and it keeps content like this coming. Now, settle in, get yourself nice and comfortable. Let's begin. A generation ship is not a spacecraft in any conventional sense. It is a world, a fully enclosed, self-sustaining habitat designed to carry a human population across the void between stars over a journey lasting not years or decades but centuries, potentially millennia. The passengers who depart Earth would never arrive at the destination. Their children would not arrive. Their grandchildren might not arrive. The people who eventually step onto an alien world would be the distant descendants of the original crew, born and raised entirely within the walls of a vessel they never chose to board. They would know Earth only as a word in a history archive. The sky they grew up under would be a ceiling. The ground beneath their feet would be a floor bolted to a superstructure, hurtling through absolute darkness at velocities that would seem both tremendous and pathetically inadequate, depending on whether you measured them against human experience or against the distances involved. This concept exists because physics imposes a constraint on interstellar ambition so brutal that it eliminates every shortcut the human imagination has ever invented. The speed of light is not merely fast, it is the absolute upper boundary on how quickly information, matter, or energy can traverse space. Nothing with mass can reach it. Nothing can exceed it. This is not a technological limitation awaiting a clever workaround. It is woven into the structure of space-time itself, confirmed by over a century of experimental evidence spanning particle accelerators, satellite-based atomic clocks, and observations of relativistic jets erupting from black holes. Every film and novel that casually depicts faster-than-light travel is invoking physics that does not exist in our universe. Warp drives require exotic matter with negative energy density, a substance that has never been observed or produced. Wormholes require stabilization mechanisms that violate known energy conditions. Hyperspace has no analogue in confirmed physical theory. These remain mathematical curiosities, not engineering prospects. This means interstellar travel, if it ever happens, must occur at speeds dramatically below light speed. And the moment you accept that constraint, the distances involved become devastating. The nearest star system to our Sun is Alpha Centauri, a triple star system located approximately 4.37 light-years away. A light-year equals roughly 5.88 trillion miles. In total, Alpha Centauri lies about 25.6 trillion miles from Earth. To put that in human terms, consider the fastest spacecraft humanity has ever launched. The Parker Solar Probe, during its closest solar approaches, has reached velocities of approximately 430,000 miles per hour, making it the fastest human-built object in history. If you could somehow sustain that velocity in a straight line toward Alpha Centauri, the journey would take roughly 6,800 years. That is longer than the span separating modern civilization from the construction of the earliest known cities in Mesopotamia. You would depart Earth before the invention of writing and arrive after a duration that encompasses every empire, every war, every scientific revolution, and every cultural transformation in the entire recorded human story, multiplied by a factor of roughly 2. But Alpha Centauri is the closest system. It sits practically on our doorstep in galactic terms. Most stars of scientific interest lie considerably farther away. Tau Ceti, a sun-like star with confirmed planetary candidates that has drawn attention from astronomers searching for potentially habitable worlds, sits approximately 11.9 light-years from Earth. At Parker Solar Probe speeds, the trip would take approximately 19,000 years. The TRAPPIST-1 system, which generated extraordinary scientific excitement when astronomers confirmed it contains 7 rocky planets, 3 of them orbiting within the star's habitable zone, lies roughly 39.5 light-years away. Reaching TRAPPIST-1 at our current best speed would require approximately 63,000 years. That is a span so vast it equals roughly 1/5 of the entire time anatomically modern Homo sapiens has existed as a species, compressed into a single unbroken voyage. These are not exaggerations crafted for dramatic effect. They are confirmed calculations derived from measured distances and achieved velocities. They represent the stark foundation upon which every generation ship proposal must be built. The most commonly discussed propulsion concepts for interstellar missions fall into several categories, each carrying severe limitations that constrain achievable velocities far below the speed of light. Chemical rockets, the technology that carried Apollo astronauts to the moon and that currently launches every satellite and space station module into orbit, are essentially useless for interstellar travel. The fundamental constraint is exhaust velocity. A chemical rocket expels combustion products at roughly 3 to 4.5 kilometers per second. The Tsiolkovsky rocket equation, the foundational relationship governing all rocket propulsion, dictates that reaching higher velocities requires exponentially increasing fuel mass. A chemical rocket attempting to accelerate a payload to even 1% of light speed, approximately 3,000 kilometers per second, would require a fuel-to-payload mass ratio so astronomical that the fuel mass would exceed the mass of the observable universe many times over. The mathematics is not merely unfavorable, it is physically absurd. Nuclear thermal propulsion offers better performance. By heating a propellant, typically hydrogen, through the core of a nuclear fission reactor, exhaust velocities roughly double compared to the best chemical rockets, reaching approximately 8 to 9 kilometers per second. NASA tested nuclear thermal engines extensively during the 1960s under Project Nerva, successfully firing reactor-powered engines that demonstrated the concept works. Modern successors to this technology are under active development, but even nuclear thermal rockets cannot achieve the velocities needed for practical interstellar transit. A nuclear thermal vessel might reach speeds of perhaps 50 to 100 kilometers per second with optimized staging. That sounds fast until you compare it to the 3,000 kilometers per second that represents 1% of light speed. Nuclear thermal propulsion falls short by a factor of 30 to 60. It could revolutionize travel within our solar system, while remaining hopelessly inadequate for reaching even the nearest star in any reasonable time frame. Nuclear pulse propulsion represents a dramatic escalation in ambition. The concept, studied under Project Orion beginning in 1958, proposed detonating nuclear explosives behind a massive pusher plate attached to the spacecraft. Each detonation would vaporize a propellant material and accelerate the resulting plasma against the plate, generating enormous thrust impulses. Freeman Dyson and other physicists involved in the study estimated that an Orion-type vessel could theoretically achieve velocities of 3 to 5% of light speed. More optimistic variants using fusion explosives and advanced staging concepts suggested velocities as high as 10% of light speed might be attainable. At 5% of light speed, the journey to Alpha Centauri contracts to roughly 87 years. That is within a single extended human lifetime, potentially achievable without generational turnover if departing crew members are young enough at launch. The concept begins to look almost reasonable for the nearest stars. but extending the calculation to more distant targets reintroduces the generation ship problem with full force. At 5% of light speed, reaching Tau Ceti requires approximately 240 years. Reaching TRAPPIST-1 requires approximately 790 years. Multiple complete generations would live their entire lives aboard the vessel between departure and arrival. At 1% of light speed, a more conservative but perhaps more realistic estimate for near-future propulsion capability, the numbers become stark. Alpha Centauri requires approximately 437 years. Tau Ceti requires roughly 1,190 years. TRAPPIST-1 demands approximately 3,950 years. These are mission durations measured not in human lifetimes but in civilizational epochs. More advanced propulsion concepts exist in theoretical literature. Fusion propulsion, if sustained ignition and net energy gain are ever achieved in a compact and throttleable engine, could theoretically deliver higher exhaust velocities than fission-based systems. Specific impulse values for deuterium-helium-3 fusion have been estimated in the range of 100,000 seconds, roughly 10 times better than nuclear thermal rockets. But sustained nuclear fusion remains an unsolved engineering challenge on Earth. Decades of effort and tens of billions of dollars in research funding have not yet produced a single reactor capable of continuous net energy output. Assuming fusion propulsion will be available for a generation ship means assuming a technological breakthrough of the first magnitude, one that is plausible but by no means guaranteed. Beamed propulsion systems offer a different approach entirely. Rather than carrying fuel, a spacecraft would be accelerated by an external energy source, typically a powerful laser or microwave array located in the home solar system, pushing against a large reflective sail attached to the vessel. The Breakthrough Starshot Initiative, funded by Yuri Milner and endorsed by numerous prominent physicists, proposes accelerating gram-scale probes to approximately 20% of light speed using a ground-based laser array with a combined power output of roughly 100 gigawatts. At that velocity, a tiny probe could reach Alpha Centauri in approximately 20 years. The concept is elegant for small probes, scaling it to a vessel carrying thousands of humans with functional ecosystems, agricultural capacity, industrial workshops, and all the infrastructure needed for multi-generational habitation is an entirely different proposition. The energy required to accelerate a payload scales linearly with mass. A generation ship massing even 100,000 metric tons, a conservative estimate, would require roughly 100 billion times more energy to accelerate than a gram-scale probe. The laser array needed to push such a vessel would need to output power comparable to the total energy production of a small star, sustained over a period of years to decades during the acceleration phase. This is not a technology gap. It is a chasm measured in orders of magnitude that no foreseeable engineering advancement is likely to bridge. The most realistic propulsion scenarios for a crewed interstellar vessel, grounded in known physics rather than speculative breakthroughs, place achievable velocities somewhere between 1 and 5% of light speed. These numbers are themselves optimistic. They assume propulsion technologies that do not yet exist in functional, tested form, but that operate on principles confirmed by experimental physics. Using this velocity range, the travel time to neighbouring star systems spans from roughly 100 years for the closest targets under the most favourable assumptions to several thousand years for systems of meaningful scientific interest under more conservative projections. The implications of these timescales are difficult to overstate. No human-built structure has ever been required to function continuously for even 500 years. The oldest surviving buildings on Earth, ancient stone temples, pyramids, and fortifications, are static structures. They have no moving parts. They require no power generation, no atmospheric regulation, no water recycling, and no biological life support. They sit passively on the surface of a geologically stable planet with a breathable atmosphere and a functional biosphere providing all necessary environmental services. Their survival over millennia is a testament to the durability of stone under benign conditions. It says nothing about the durability of complex machinery under hostile ones. A generation ship must perform the opposite of passive endurance. It must actively sustain interlocking systems of machinery, ecology, and human society every second of every day, for longer than most civilizations have persisted. Ancient Egypt endured for approximately 3,000 years. The dynastic history of Imperial China spans a comparable duration. A generation ship traveling to TRAPPIST-1 at 1% of light speed would need to function reliably for longer than either. A generation ship traveling to TRAPPIST-1 at 1% of light speed would need to function reliably for longer than either of these civilizations existed, and it would need to do so without access to the planetary resources, geographic diversity, and population reserves that allowed those civilizations to recover from setbacks. Consider the physical scale of the vessel required. Proposals vary depending on assumptions about population size, mission duration, and propulsion technology. But most serious engineering studies converge on broadly similar parameters. A generation ship must house a population large enough to maintain genetic diversity, which research suggests requires a minimum of several hundred to several thousand individuals depending on mating patterns and acceptable levels of inbreeding risk. Those people need living space sufficient to prevent psychological degradation, food production systems capable of sustained caloric output across centuries, water recycling infrastructure with near-perfect recovery rates, atmospheric management maintaining breathable composition within narrow tolerances, medical facilities equipped for every condition, from dental emergencies to cancer treatment, educational systems, preserving technical knowledge across generations, manufacturing capacity sufficient to produce replacement components for critical machinery, and recreational spaces adequate to sustain mental health across lifetimes of confinement. The most detailed engineering study of an interstellar vessel concept was the British Interplanetary Society's Project Daedalus, conducted in the 1970s and later updated as Project Icarus. These studies focused primarily on the propulsion challenge rather than long-duration habitation, but they established that even an unmanned interstellar probe would require a vessel massing approximately 50,000 metric tons, most of that being fuel. A crewed vessel carrying full life support, agricultural systems, manufacturing facilities, and sufficient structural mass for radiation shielding has been estimated in various studies to require total masses ranging from 500,000 to 10 million metric tons, depending on population size, mission duration, and shielding strategy. For context, the largest structure humans have ever assembled in orbit masses approximately 420 metric tons. A generation ship at the low end of estimates would mass roughly 1,200 times more. At the high end, perhaps 24,000 times more. At the upper end, perhaps 24,000 times more. The industrial effort required to construct such a vessel in space would dwarf every large-scale engineering project in human history combined. The Apollo program, adjusted for inflation, cost roughly $250 to $280 billion and required the focused efforts of over 400,000 workers across a decade. A generation ship would likely demand resources measured in significant fractions of global GDP sustained over decades of construction. But construction, monumental as it would be, is not the primary obstacle. The primary obstacle is what happens after the vessel departs the solar system. The moment a generation ship crosses beyond practical resupply range from Earth, it becomes permanently severed from the industrial base, supply chains, raw material extraction networks, and accumulated technological infrastructure of human civilization. Every atom of structural material, every spare component, every litre of water, every seed, every microorganism in the soil of its agricultural systems represents the total material endowment for the remainder of the mission. There are no additional shipments. There is no emergency resupply. There is no rescue mission. If a critical system fails and cannot be repaired using materials already aboard, the consequences propagate through every dependent system with the inevitability of falling dominoes. This interdependence is worth examining carefully because it defines the fragility of the entire enterprise. Atmospheric processing depends on continuous power generation. Without electricity, carbon dioxide scrubbers stop functioning, oxygen generation ceases, and the air becomes lethal within days to weeks depending on the enclosed volume and population size. Food production depends on atmospheric processing, providing appropriate gas mixtures for plant growth, on thermal regulation, maintaining temperatures within biological tolerances, on lighting systems supplying photosynthetically active radiation, and on water delivery systems providing nutrient solutions to hydroponic or aeroponic growing beds. Water recycling depends on power, on functional filtration membranes, on chemical treatment systems, and on the biological waste streams from food production and human metabolism. Human survival depends on all of the above functioning simultaneously and continuously. A failure in any single link cascades downstream into every dependent process. This web of dependencies must hold together not for a mission of years, not for a mission of decades, but for longer than any dynasty, any religion, any language, any cultural tradition in human history has persisted without fundamental transformation. The question is not whether the engineering is difficult. Humanity has demonstrated extraordinary engineering capability. The question is whether the physics of material degradation, the biology of closed ecosystems, and the mathematics of compounding failure probabilities permit any engineering solution to remain functional across such timescales. The generation ship concept did not emerge from optimism about human engineering prowess. It emerged from desperation about the physics of distance. The generation ship exists as a concept because the speed of light is absolute, because the distances between stars are measured in units that render human experience irrelevant, and because no known physics offers a shortcut. It is not a celebration of capability. It is an acknowledgement of limitation. It says, we cannot cross the void quickly, so perhaps we can endure it slowly, carrying everything necessary for survival inside a sealed vessel, and hoping that the systems hold. The word hoping is doing significant work in that sentence, because what separates the generation ship from every other engineering challenge humanity has faced is the timescale. We build bridges designed to last 100 years with regular maintenance. We build nuclear reactors designed to operate for 40 to 60 years with scheduled refurbishment. We build spacecraft designed to function for 15 to 20 years with resupply from Earth. Each of these represents an extraordinary achievement. None of them comes close to the operational lifetime a generation ship would require. The engineering community has a term for the long-term reliability challenge. It is called mean time between failures, and it quantifies the average interval between breakdowns for any given component. For a simple mechanical bearing, this might be 50,000 hours. For a high-reliability electronic control system, perhaps 200,000 hours. These numbers sound reassuring until you convert them into years and multiply by the number of critical components aboard a complex vessel. 50,000 hours is approximately 5.7 years. A generation ship operating for 500 years would need to replace or rebuild that bearing approximately 88 times for every critical component. With no factory to produce replacements and no supply chain to deliver raw materials, the generation ship is humanity's most ambitious theoretical response to the most humbling physical reality we have ever confronted: the sheer, overwhelming emptiness between the stars. It proposes that if we cannot conquer distance through speed, we can survive it through endurance. But endurance on this scale has never been tested, never demonstrated, and never even approximated by any human system. Everything that follows in this story examines whether that endurance is physically possible, or whether the universe has placed a barrier between the stars that is measured not in miles but in time. The first and most relentless enemy any generation ship would face is already familiar to every engineer who has ever inspected a corroded weld or replaced a cracked turbine blade: the quiet, patient, inevitable degradation of every material and every machine aboard, hour by hour, year by year, century by century, with no factory on any horizon to rebuild what entropy destroys. Every manufactured substance has a lifespan. Steel corrodes, aluminum fatigues. Steel corrodes, aluminum fatigues. Polymers crack under ultraviolet exposure. Copper oxidizes. Rubber hardens and becomes brittle. Lubricants break down into sludge. Solder joints develop whiskers of crystalline tin that short-circuit electronics. Seals compress and lose elasticity. Welds develop stress concentrations that propagate into fractures. These processes are not manufacturing defects. They are not signs of poor workmanship. They are consequences of the second law of thermodynamics operating at the molecular level. Ordered atomic arrangements move toward disordered ones. Chemical bonds break, crystal structures shift. Entropy increases, always, everywhere, without exception, and it never reverses itself spontaneously. On Earth, we manage this reality through a strategy so pervasive it has become invisible to daily life. We replace things. When a water main corrodes through, a municipal crew excavates the street, removes the failed section, and installs a new pipe manufactured from raw materials extracted from mines, processed in smelters, and delivered by a transportation network spanning thousands of miles. When a turbine blade in a jet engine develops fatigue cracks after its rated number of flight cycles, a maintenance crew removes it and bolts in a replacement produced by a specialized foundry using single crystal casting techniques perfected over decades of metallurgical research. The entire edifice of modern technological civilization rests on the assumption that degraded components can be swapped for new ones, drawn from a functionally unlimited reservoir of raw materials, manufacturing infrastructure, and specialized expertise. A generation ship carries no such reservoir. It departs with a finite inventory of materials, and that inventory represents the total material budget for the remainder of the voyage. There are no mines. There are no ore deposits. There are no geological formations to quarry. There is no biosphere producing timber or fiber. Every kilogram of steel, every gram of silicon, every milligram of rare earth element loaded aboard at departure is every kilogram, every gram, every milligram that will ever be available until arrival. Nothing enters the system from outside. The interstellar medium, the thin haze of atoms drifting between stars, contains roughly 1 hydrogen atom per cubic centimeter. Collecting meaningful quantities of material from this diffuse gas while traveling at several % of light speed would require collection scoops of planetary scale, a concept that collapses under its own engineering absurdity. This closed material budget transforms every engineering problem from a question of capability into a question of duration. Humanity knows how to build machines that function. We do not know how to build machines that function for 1,000 years without external resupply. Consider the structural skeleton of the vessel first. A generation ship's hull and internal framework must bear mechanical loads continuously for the entire mission duration. If the vessel rotates to generate artificial gravity through centripetal acceleration, the most commonly proposed method for avoiding the devastating physiological effects of prolonged weightlessness, structural members experience cyclical loading with every revolution. A habitat module rotating once per minute to produce approximately 1 standard gravity at its rim subjects its structural elements to a complete stress cycle every 60 seconds. That equals 1,440 cycles per day, 525,600 cycles per year. Over a century, 52.56 million cycles. Over 500 years, 262.8 million. Over a millennium, 525.6 million. Metal fatigue under cyclical loading is among the most exhaustively studied failure modes in materials science. The phenomenon was first identified in the 19th century after a series of catastrophic railway axle failures, and it has been responsible for some of the most infamous structural disasters in engineering history, from the de Havilland Comet aircraft disintegrations of the 1950s to the Aloha Airlines fuselage rupture of 1988. The mechanism is well understood. Microscopic cracks initiate at stress concentration points, grain boundaries, surface imperfections, or inclusion sites within the metal. Each stress cycle advances the crack front by a tiny increment. The crack grows invisibly for thousands or millions of cycles until it reaches a critical length at which the remaining cross-section can no longer support the applied load. At that point, the component fractures, often with catastrophic speed and little warning. Modern aerospace engineering manages fatigue through inspection-based maintenance programs. Aircraft structures are designed with specific fatigue lives, typically measured in tens of thousands of flight cycles or tens of thousands of pressurization cycles. Components are inspected at scheduled intervals using ultrasonic testing, eddy current methods, or radiographic imaging. When cracks are detected or when components reach their rated fatigue life, they are replaced. This system works because the replacement components exist, produced by a functioning manufacturing base with access to raw materials and specialized fabrication equipment. Aboard a generation ship, inspection remains possible, but replacement becomes progressively more difficult as the mission ages and spare material inventories deplete. A cracked structural beam in year 50 might be replaced from stockpiled reserves. A cracked beam in year 500 might require scavenging material from a less critical structure. A cracked beam in year 900 might have no replacement available at all, forcing the crew to accept a weakened structure or abandon an entire habitat section. Titanium alloys, among the most fatigue-resistant structural materials available to modern engineering, demonstrate endurance limits under laboratory conditions that are typically characterized out to 10 million cycles. Beyond that threshold, the data becomes increasingly sparse because few testing programs run longer. Extrapolating fatigue behavior to hundreds of millions of cycles introduces uncertainties that materials scientists acknowledge but cannot currently resolve. The material might endure, it might not. The honest answer is that nobody knows because nobody has ever needed to know. No terrestrial structure has ever been required to sustain cyclical loading for centuries without maintenance. Access to fresh material. Radiation damage to structural materials compounds the fatigue problem through an entirely separate degradation pathway. In interstellar space, beyond the protective influence of any star's magnetic field, the vessel would be continuously bombarded by galactic cosmic rays. These are not the relatively benign particles that constitute most solar wind. Galactic cosmic rays include protons accelerated to enormous energies, helium nuclei, and heavier ions up to and including iron nuclei travelling at substantial fractions of light speed. The most energetic among them carry kinetic energies that exceed anything achievable in terrestrial particle accelerators. When a high-energy cosmic ray strikes an atom in a metal lattice, it displaces that atom from its equilibrium position, creating what physicists call a Frenkel pair, a vacancy where the atom was and an interstitial where it landed. A single high-energy particle can create cascades of displacements, knocking atoms into neighbouring atoms in a billiard ball chain reaction that produces clusters of defects. Over time, these displacement defects accumulate. They migrate through the lattice and aggregate into larger structures, voids, dislocation loops, and precipitate clusters that alter the material's mechanical properties. The macroscopic consequence is a phenomenon called radiation embrittlement. The material becomes harder, meaning it resists deformation more strongly, but simultaneously becomes less tough, meaning it fractures more readily. Once deformation begins, ductile materials that could originally bend and flex under load become brittle materials that crack and shatter. This transformation has been extensively studied in nuclear reactor pressure vessels, where neutron bombardment produces analogous displacement damage over operational lifetimes of 40 to 60 years. The galactic cosmic ray environment in interstellar space delivers an unshielded dose rate of approximately 300 to 400 millisieverts per year to material surfaces. This figure comes from measurements by instruments aboard spacecraft operating beyond Earth's magnetosphere, confirmed by models of the galactic cosmic ray spectrum maintained by NASA and the European Space Agency. Over a century, the cumulative absorbed dose in structural components reaches 30 to 40 sieverts. Over a millennium, 300 to 400 sieverts. For comparison, the threshold dose at which measurable embrittlement appears in reactor pressure vessel steels is approximately 1 to 10 displacements per atom, a metric that depends on material composition and temperature, but that cosmic ray bombardment would approach over multi-century timescales in unshielded structures. The critical interaction between fatigue and radiation damage deserves emphasis because the two processes reinforce each other. Radiation embrittlement makes materials more susceptible to fatigue crack propagation. Fatigue cracks create stress concentrations that make radiation-damaged zones more likely to fracture. A structural member experiencing simultaneous cyclical loading and continuous radiation exposure degrades faster than either process alone would predict. The combined effect is synergistic, not merely additive, and it has been confirmed in studies of irradiated steel specimens subjected to fatigue testing. Micrometeorite bombardment adds a third degradation pathway to the hull. Interstellar space is not a perfect vacuum. It contains dust grains ranging in mass from femtograms to milligrams, remnants of stellar outflows, supernova ejecta, and cometary debris distributed thinly throughout the galactic disk. A vessel travelling at 3% of light speed, approximately 9,000 kilometers per second, encounters these particles at relative velocities far exceeding anything experienced in the solar system. At such speeds, a dust grain massing 1 microgram carries kinetic energy equivalent to several joules, sufficient to excavate a small crater in metal. A grain massing 1 milligram impacts with the energy of a rifle bullet. The cumulative effect of sustained micrometeorite bombardment is surface erosion. Each impact creates a crater, and each crater acts as a stress concentration point that accelerates fatigue crack initiation. Over decades and centuries, the outer hull surface develops a progressively roughened texture, pockmarked with impact sites of varying size. Whipple shield configurations, using an outer sacrificial bumper spaced away from the pressure hull to vaporize incoming particles before they reach critical structures, mitigate individual impacts effectively. But the bumper layer itself erodes under sustained bombardment. Its effectiveness diminishes over time unless it can be repaired or replaced, which returns to the fundamental constraint of finite material reserves. Power generation represents the metabolic heartbeat of any generation ship. Without continuous electrical power, atmospheric processing halts, temperature regulation ceases, water recycling stops, food production lighting extinguishes, and the computational systems managing all other operations go dark. Every other subsystem depends on power. A generation ship's power system is therefore the single point whose failure guarantees mission termination, and it must function without interruption for the full duration of the voyage. Nuclear fission is the most technologically mature option for deep space power generation. Fission reactors have operated in space, notably aboard Soviet Buk and Topaz satellites and in American SNAP program test flights. The physics is proven. The engineering challenges are well characterized. Modern compact fission reactor designs, such as NASA's Kilopower project, which successfully demonstrated a prototype in 2018, show that kilowatt-scale reactors using uranium-235 fuel and Stirling cycle generators can function reliably in space environments. But terrestrial fission reactors, operating under far more benign conditions with access to regular maintenance and component replacement, have operational lifetimes of 40 to 60 years. Beyond that, neutron irradiation has embrittled the reactor pressure vessel to the point where continued operation poses unacceptable fracture risk. Fuel cladding has degraded, control rod mechanisms have worn, instrumentation has drifted. The reactor is not broken in a dramatic sense. It has simply aged beyond the point where its continued operation can be guaranteed safe. Extending a fission reactor's functional lifetime to several centuries would require overcoming material degradation challenges that the nuclear industry has managed for decades exclusively through component replacement. The reactor vessel cannot be replaced aboard a generation ship, The fuel cladding cannot be remanufactured from fresh zirconium alloy. The control systems cannot be rebuilt using electronics fabricated in a state-of-the-art semiconductor foundry. Whatever the reactor consists of at departure is what it must consist of for the duration of operation. Fuel supply imposes an additional constraint. A fission reactor consuming enriched uranium at a rate sufficient to power a generation ship's full electrical load, estimated by various studies at 50 to several hundred megawatts. Thermal, depending on population size and agricultural energy requirements, would consume its fuel inventory on timescales of decades to perhaps a century or two, depending on reactor design and enrichment level. Breeder reactor configurations that transmute fertile uranium-238 into fissile plutonium-239 could extend the fuel supply substantially, potentially by factors of 50 or more. But breeder reactors operate at higher temperatures, use more corrosive coolants such as liquid sodium, and demand more sophisticated fuel reprocessing capability. Each of these characteristics accelerates material degradation and increases operational complexity. Radioisotope thermoelectric generators, the power source sustaining humanity's most distant operational probes for decades, offer extraordinary reliability due to their complete absence of moving parts. A radioisotope generator produces electricity through the Seebeck effect, converting heat from radioactive decay directly into voltage across a thermoelectric junction. No turbines, no pumps, no working fluids, but their power output decays with the half-life of the fuel isotope. Plutonium-238, the standard RTG fuel, has a half-life of 87.7 years. After one half-life, output drops to 50%. After two half-lives, 25%. After three, 12.5%. An RTG-powered generation ship would face steadily diminishing power budgets that would force progressive shutdown of non-essential systems over the course of centuries, a slow strangulation by radioactive decay curves that no engineering intervention can alter. Fusion power remains the theoretical ideal. Deuterium-tritium or deuterium-helium-3 fusion reactions release energy densities millions of times greater than chemical fuels and tens of times greater than fission, with fuel isotopes that could be carried in manageable quantities for millennia of operation. A functioning fusion reactor would effectively solve the power generation longevity problem, but as of the mid-2020s, no fusion reactor on Earth has achieved sustained net energy gain. The engineering challenges of plasma confinement, materials compatibility with 14 mega-electron-volt neutron bombardment, and tritium breeding remain formidable despite decades of concentrated research effort. Projecting that fusion power will be available for a generation ship requires projecting a breakthrough that has not yet occurred, and planning a mission around an assumed breakthrough is a fundamentally different exercise than planning around demonstrated technology. Life support machinery faces the same longevity constraints as power systems, multiplied by greater mechanical complexity. The systems that maintain breathable atmosphere, potable water, and stable temperature aboard any crewed spacecraft are intricate assemblages of pumps, fans, compressors, heat exchangers, catalytic reactors, membrane filters, condensers, and electronic controllers, each one subject to wear, corrosion, fouling, and eventual failure. Consider a single critical subsystem, the carbon dioxide removal assembly. Aboard the International Space Station, carbon dioxide is scrubbed from cabin air using zeolite molecular sieve beds that absorb carbon dioxide molecules and release them when heated. The system cycles between adsorption and desorption phases, requiring valves, heaters, fans, and control electronics operating continuously. On the ISS, this system requires regular maintenance, including replacement of check valves, fan motors, and desiccant beds, using spare parts delivered from Earth on resupply missions roughly every few months. A generation ship would need carbon dioxide removal operating not for the 15-year ISS design lifetime, but for centuries. Every valve in the system has an elastomer seal that will eventually degrade. Every fan motor has bearings that will eventually wear. Every electrical connection has a potential failure point. Multiply this by the dozens of interdependent subsystems constituting a complete life support architecture, and the maintenance burden becomes staggering. Skilled technicians with appropriate tools and materials can repair almost anything. What cannot be guaranteed is that the supply of replacement materials, the availability of specialized tools, and the depth of technical expertise can be sustained across generational timescales without access to external manufacturing infrastructure. This leads to what may be the most underappreciated constraint on generation ship viability: the manufacturing bottleneck. Modern technological civilization depends on supply chains of extraordinary depth and specialization. A single integrated circuit, the kind found in any household appliance, requires photolithographic equipment that costs billions of dollars, ultra-pure silicon refined through dozens of chemical processing steps, photoresist chemicals synthesized from petroleum precursors, dopant gases of extreme purity, and cleanroom environments maintained to particle counts below 10 per cubic meter. The knowledge required to operate this equipment is held by specialists who train for years in institutions supported by research universities, national laboratories, and corporate research divisions representing centuries of accumulated expertise. A generation ship cannot carry a complete semiconductor fabrication facility. The mass, volume, power consumption, and chemical feedstock requirements are prohibitive. It could carry stockpiles of replacement electronics, sufficient for some period of time, but those stockpiles are finite. When the last spare processor fails and no replacement can be manufactured aboard, the computational capability it provided is permanently lost. When the last spare sensor drifts beyond calibration limits and no recalibration standard can be produced, the measurement capability it provided is permanently lost. This principle extends to every manufactured component aboard. Precision machining requires machine tools. Machine tools require cutting inserts made from tungsten carbide or ceramic materials. Those inserts wear out and must be replaced. Replacement requires either stockpiled spares or the ability to manufacture new inserts from raw tungsten and carbon feedstocks using powder metallurgy techniques. Powder metallurgy requires furnaces, presses, and sintering equipment, each with its own maintenance demands and material requirements. The manufacturing chain is recursive. Every tool needed to make a component requires other tools to make it. Those tools require still other tools. On Earth, this recursion terminates at the mining and refining industries, which extract raw materials from geological deposits using energy from combustion or nuclear sources. Aboard a generation ship, the recursion terminates at whatever raw material stockpiles were loaded at departure. When those stockpiles are exhausted, the manufacturing chain breaks at its foundation, and every downstream capability that depended on it degrades irreversibly. What makes this recursion so dangerous is that the regression does not announce itself as a single dramatic event. It manifests as a slow step descent through plateaus of diminishing capability, each step appearing manageable in isolation, each step permanently foreclosing options that previous generations took for granted. Consider a plausible sequence. In the first century, the ship's electronic stockpile depletes. Processors, sensors, and control boards that fail can no longer be replaced with factory-quality equivalents. The crew adapts by cannibalizing non-critical systems, stripping processors from entertainment terminals to replace failed units in atmospheric monitoring. Computational capacity contracts. Systems that once operated under automated oversight shift to manual monitoring, demanding more crew hours for the same level of safety coverage. The ship still functions, but it functions the way a household functions after a power cut, with human attention substituting for automated convenience. And human attention is a finite resource that tires, errs, and sleeps. In the second century, the precision machining capability degrades. The cutting inserts for the ship's lathes and milling machines have worn through their stockpiles. Replacement inserts fabricated from recycled materials lack the hardness and dimensional precision of the originals. The tolerances achievable in the machine shop widen. Components that once fit to within thousandths of a centimetre now fit to within hundredths. Pump impellers run slightly off balance. Valve seats do not seal as tightly. Pipe joints weep where they once held firm. None of these imprecisions is individually catastrophic. Each one incrementally increases the failure rate of the systems those components serve, and each one is permanent because the capability to do better no longer exists aboard. In the 3rd century, the chemical feedstock reserves thin. Lubricants can no longer be synthesized to original specifications because the precursor chemicals are exhausted. Substitute lubricants formulated from available organic stocks perform adequately at room temperature but break down faster under the elevated temperatures inside reactor cooling loops and turbine housings. Bearing wear accelerates. Seal degradation accelerates. The maintenance interval for critical rotating machinery shortens from years to months, consuming spare parts faster and demanding more frequent interventions from a crew whose machining capability is already degraded. Each plateau feels stable to the generation living on it. They have never known the capabilities that were lost before their time. The engineers of the 3rd century do not mourn the precision machining of the 1st century because they never experienced it. They work competently within the constraints they inherited, unaware that those constraints are tighter than the constraints their grandparents faced, which were tighter than the constraints their great-grandparents faced. The regression is invisible from the inside. It is visible only from the outside, across the full arc of centuries, and there is nobody on the outside to see it. This is the technological equivalent of boiling a frog. No single generation experiences a crisis sharp enough to trigger emergency measures. Each generation simply operates at a slightly lower level of capability than the one before, normalizing the decline as baseline, passing a diminished inheritance to their successors who will diminish it further. The ship does not fail. It forgets what it was once capable of, one manufacturing process at a time, one material specification at a time, one tolerance threshold at a time, until the gap between what its systems require and what its workshops can provide becomes unbridgeable. 3-dimensional printing and additive manufacturing technologies offer partial mitigation. A versatile fabrication system capable of producing components from recycled metal feedstocks could extend the maintenance window significantly. But additive manufacturing has limitations. Printed metal components typically exhibit inferior fatigue properties compared to wrought or forged equivalents due to residual porosity and anisotropic microstructures. The range of materials printable by any single system is restricted, and the printing equipment itself degrades, requiring maintenance and eventual replacement of laser sources, build platforms, powder handling mechanisms, and control electronics. The overarching pattern is recursive degradation. Systems degrade. The systems that repair degraded systems also degrade. The systems that maintain the repair systems degrade as well. Each layer of this maintenance hierarchy draws from the same finite material and energy budget. Over centuries, the budget shrinks while the maintenance demands grow. Redundancy, the standard engineering response to reliability requirements, provides a buffer against this process but does not eliminate it. Triple redundancy means 3 independent copies of a critical system. If one fails, 2 remain. If a second fails, 1 remains. Each failure consumes a layer of safety margin. Over centuries of continuous operation, redundancy is gradually spent. A system that began with triple redundancy in year 1 might have double redundancy by year 100, single redundancy by year 300, and no redundancy by year 500. At that point, the next failure of that system is the last. The rate at which redundancy is consumed depends on the failure rates of individual components and the repair rates achievable with dwindling resources. Early in the mission, when spare parts are abundant, technicians are well trained, and documentation is comprehensive, repair rates may exceed failure rates comfortably. The ship operates with wide safety margins. Decades pass without crisis, but the trend is unidirectional. Failure rates increase as components age. Repair rates decrease as spare inventories deplete and specialized knowledge potentially erodes. At some point, these two curves cross. After that crossing, the ship is consuming its safety margins faster than it can rebuild them. The timeline for this crossover depends entirely on design quality, initial material reserves, crew competence, and a measure of statistical fortune. For a mission lasting 1 to 2 centuries, meticulous design and generous provisioning might sustain adequate safety margins throughout. For a mission lasting 5 centuries, the crossover becomes likely. For a mission lasting a millennium, it becomes virtually certain under any realistic set of assumptions. None of this analysis relies on dramatic events. No asteroid strike, no sabotage, no catastrophic explosion. The degradation described here is quiet, gradual, and thermodynamically inevitable. It is the sound of a bearing slowly wearing against its race, the sight of a seal imperceptibly flattening under compression, the invisible migration of displaced atoms through an irradiated crystal lattice. Each process is individually slow. Collectively, over centuries, they are unceasing. The engineering challenge of a generation ship is not building a vessel that works on the day it launches. Human engineers are magnificently skilled at that. The challenge is building a vessel that still works on the day it arrives, centuries or millennia later, after every material has been irradiated, every mechanism has cycled millions of times, every seal has compressed, every lubricant has decomposed, and every spare part has been used. This is a challenge that no engineering tradition in human history has ever faced, and the physics of material degradation offers no reason to believe that any design, however brilliant, can indefinitely outrun the second law of thermodynamics inside a closed system with finite resources. But entropy does not confine itself to metal and circuitry. The living systems inside the hull, the ecosystems, the genomes, the societies, face the same merciless timeline that threatens every rivet and reactor in the hull. In 1991, 8 researchers walked into a sealed glass structure in the Arizona desert and closed the door behind them. Biosphere 2 was the most ambitious closed ecosystem experiment ever attempted on Earth. Spanning 3.14 acres under a lattice of glass and steel, it contained a miniature ocean with a coral reef, a tropical rainforest, a fog desert, a savanna grassland, a mangrove wetland, and an intensive agricultural zone. The designers had spent approximately $150 million engineering a system intended to recycle its own atmosphere, water, and nutrients indefinitely, sustaining 8 human beings without any material exchange with the outside world. The project was meant to last 2 years. It was meant to prove that humans could maintain a self-sustaining biosphere inside a sealed enclosure, a necessary precondition for any serious discussion of generation ships or off-world colonization. Within 16 months, the experiment was in crisis. Oxygen levels plummeted from the standard 21% to 14.2%, equivalent to breathing at an altitude of approximately 13,400 feet. At that concentration, the crew experienced chronic fatigue, impaired cognitive function, and difficulty performing physical labor. The cause was eventually traced to an interaction nobody had predicted. Soil microorganisms, billions of them teeming in the agricultural beds and rainforest floor, were consuming oxygen through aerobic respiration at rates far exceeding the photosynthetic output of the plants. Simultaneously, exposed concrete in the structure's foundation was absorbing oxygen through carbonation reactions, quietly sequestering molecules that the biosphere needed for human survival. 2 separate processes, one biological and one chemical, were draining the atmosphere through mechanisms that had been overlooked during years of design and testing. Carbon dioxide fluctuated erratically. Nitrous oxide, a potent neurotoxin at elevated concentrations, accumulated to levels that measurably impaired brain function. Morning glory vines, freed from the ecological checks that controlled them in natural environments, overran the agricultural zone and choked out food crops. 19 of 25 vertebrate species introduced into the system went extinct. All pollinating insects died, eliminating natural reproduction for any plant species dependent on insect pollination. Cockroach and ant populations, liberated from predators that had perished, exploded into infestations. The crew lost significant body weight from caloric insufficiency. Interpersonal conflicts escalated until the group fractured into two factions that communicated only through intermediaries. Emergency oxygen injections from outside were required to keep the crew alive. The seal was effectively broken. The experiment continued in a modified form, but the original premise, complete material closure, had failed. This failure illuminated a principle that carries devastating implications for generation ship concepts. Closed ecosystems are not merely difficult to sustain, they are inherently unstable at small scales. Natural ecosystems on Earth achieve their apparent stability through mechanisms that cannot be replicated inside any vessel of buildable size. Planetary ecosystems buffer disruptions through geographic scale, allowing local disturbances to be absorbed by unaffected regions thousands of miles away. They benefit from atmospheric and oceanic circulation driven by solar energy input across an entire hemisphere. They maintain biodiversity reservoirs containing millions of species, ensuring that if one functional group declines, others can partially compensate. They operate nutrient cycles involving geological processes, volcanic outgassing, tectonic subduction, and weathering of continental rock formations that unfold across timescales of millions of years. A generation ship possesses none of these buffering mechanisms. Its ecosystem is confined to a volume measured in thousands or tens of thousands of cubic meters, rather than the roughly 1 trillion cubic kilometers of Earth's biosphere. Its species inventory is limited to whatever organisms were deliberately introduced, plus whatever microorganisms hitchhiked aboard unintentionally. Its nutrient cycles must operate in perfect closure, with zero loss to geological sinks because there is no geology, and it must maintain this artificial balance not for the 2 years that defeated Biosphere 2, but for centuries. The atmospheric balance problem alone illustrates the razor-thin margins involved. Human respiration consumes oxygen and produces carbon dioxide. Plant photosynthesis reverses this exchange. In principle, the two processes balance. In practice, the balance depends on dozens of interacting variables: light intensity and duration, plant health, leaf area, soil microbial activity, temperature, humidity, nutrient availability, and carbon dioxide concentration itself, which acts as both a product of animal metabolism and a substrate for plant growth. A shift in any single variable propagates through the system, altering the equilibrium point in ways that may be difficult to predict and slow to correct. Oxygen concentration must remain within a band of approximately 16 to 23% for safe human habitation. Below 16%, physical performance deteriorates sharply. Below 12%, unconsciousness occurs within minutes. Above 25%, the flammability of virtually every organic material aboard increases dramatically, transforming a routine electrical spark into a potential conflagration. Carbon dioxide must remain below approximately 1% for long-term health. Above that threshold, chronic exposure causes headaches, impaired cognitive performance, and eventually cardiovascular stress. Above 5%, acute toxicity becomes lethal. Maintaining these concentrations within tolerance requires either mechanical atmospheric processing, which draws on the same degradation-prone machinery already shown to have finite lifespans, or biological regulation through a carefully managed plant community which introduces the instabilities demonstrated by Biosphere 2. The realistic answer is that a generation ship would need both, with mechanical systems serving as the primary buffer and biological systems providing supplemental cycling. But this means the atmospheric management system inherits the vulnerabilities of both approaches, the mechanical wear and material degradation of engineered systems combined with the ecological fragility of living systems. Water recycling presents a parallel challenge. A population of 1,000 humans requires approximately 2 to 3 cubic meters of potable water per day for drinking, food preparation, and hygiene. Agricultural systems require substantially more, perhaps 10 to 50 times the human consumption depending on crop selection and cultivation method. The total water budget for a generation ship might reach 100 to 200 cubic meters per day of circulation through various purification and recycling loops. Achieving high recycling efficiency is technically feasible. The International Space Station's water recovery system reclaims approximately 93% of wastewater, including processed urine, humidity condensate, and hygiene water. Advanced membrane distillation and catalytic oxidation systems under development target recovery rates approaching 98%. But even 98% recovery means 2% loss per cycle. Over thousands of cycles spanning years and decades, these small losses accumulate into significant deficits unless every molecule is eventually recovered. More insidiously, trace contaminants accumulate in recycled water streams. Pharmaceutical metabolites, endocrine disruptors, heavy metal ions leach from plumbing materials, and chemical byproducts of sterilization processes build up over repeated recycling passes. On the ISS, activated carbon filters and ion exchange resins remove these contaminants, but the filter media themselves are consumable, requiring periodic replacement from Earth-delivered supplies. A generation ship must either carry sufficient filter media for the entire voyage, an enormous mass penalty, or develop the ability to regenerate spent filter materials from onboard resources, a chemical engineering challenge that has not been demonstrated at the required scale and duration. Food production inside a sealed vessel demands controlled environment agriculture operating without interruption for the full mission duration. Hydroponic and aeroponic systems, in which plants grow in nutrient solutions or misted environments rather than soil, offer higher yields per unit volume than traditional farming and allow precise control of nutrient delivery. But they also introduce dependencies on mechanical systems, pumps to circulate nutrient solutions, sensors to monitor chemical composition, lighting arrays to provide photosynthetically active radiation, climate control to maintain optimal temperature and humidity, and sterilization systems to prevent pathogen accumulation in the recirculating fluid. Each of these dependencies creates a failure pathway. A pump failure interrupts nutrient delivery, a lighting array degradation reduces photosynthetic output, a sensor drift leads to incorrect nutrient concentrations, a sterilization failure permits pathogen colonization of the root zone, potentially wiping out an entire crop before the infection is identified and contained. These are not hypothetical scenarios. They are routine events in terrestrial controlled environment agriculture, managed through spare parts, replacement equipment, and access to external diagnostic expertise. Aboard a generation ship, each event must be managed using only onboard resources and onboard knowledge. Crop genetic diversity presents a subtler but equally serious long-term risk. Agricultural crops maintained in isolation gradually lose genetic variation. Without access to wild relatives or seed bank collections that refresh the gene pool, cultivated populations become increasingly homogeneous through selection pressure, genetic drift, and the simple mathematical consequence of drawing each generation's seeds from a limited parent population. Reduced genetic diversity diminishes resistance to novel pathogens, environmental stress, and changing conditions. A crop variety that begins the voyage with robust yields and disease tolerance may, after 20 or 30 generations of isolated reproduction spanning 500 to 1,000 years, become vulnerable to a pathogen strain that its ancestors would have resisted. Seed banks aboard the vessel could mitigate this risk if seeds remain viable in long-term storage, but seed viability declines over time even under optimal cold storage conditions. Most crop species maintain germination rates above 80% for 10 to 50 years under seed bank conditions. A few, notably certain cereal grains, can remain viable for over a century. But virtually no agricultural species has demonstrated reliable germination after 500 years of storage. The generation ship's agricultural genetic reserve has an expiration date, and that date almost certainly arrives before the voyage ends, for any mission lasting more than a few centuries. The agricultural challenge extends below the roots. Even hydroponic and aeroponic systems that eliminate traditional soil depend on microbial communities to function. Nutrient cycling in any food production system involves bacteria and fungi that decompose organic waste, convert nitrogen between chemical forms, solubilize phosphorus, and suppress pathogenic organisms through competitive exclusion. In terrestrial agriculture, these microbial communities are sustained by their connection to a vast planetary reservoir of microbial diversity. Soil on Earth contains roughly 10,000 distinct bacterial species per gram, drawn from a global pool numbering in the trillions of species. When a particular microbial strain declines in one field, others migrate in from surrounding environments. The system self-replenishes. Aboard a generation ship, the microbial community loaded at departure is the only microbial community that will ever exist. There is no surrounding environment to replenish lost strains. Microbial populations evolve rapidly, with generation times measured in minutes to hours rather than the decades required for human generations. Over the course of a single human year, a bacterial population can cycle through roughly 10,000 to 50,000 generations, accumulating mutations and undergoing selective sweeps that radically reshape the community's composition. Over a century, the microbial ecology of the ship's agricultural system would bear little resemblance to what was originally inoculated. Whether those evolutionary trajectories happen to maintain the nutrient cycling functions essential for crop growth is not something that can be predicted or guaranteed. Microbial communities optimize for their own reproductive fitness, not for human agricultural needs. The management of these invisible ecosystems requires microbiological expertise of a kind that is currently practiced by specialists at research universities and agricultural extension services. Monitoring microbial community composition requires DNA sequencing equipment, reagent supplies, and analytical software. Intervening when communities drift toward unfavorable configurations requires cultured reserve stocks of beneficial organisms, selective media for suppressing problematic strains, and a deep understanding of microbial ecology that takes years of graduate-level training to develop. Each of these capabilities faces the same degradation curves as every other technical capacity aboard. The scenario that should concern mission planners most viscerally is not a gradual decline in crop yields, but a sudden, catastrophic loss of a staple food source. On Earth, agricultural history is punctuated by devastating crop failures caused by pathogens exploiting genetic uniformity. The Irish potato famine of the 1840s killed roughly 1 million people and displaced another million because the Irish agricultural system depended overwhelmingly on a single potato variety, the Irish lumper, which proved uniformly susceptible to the water mold Phytophthora infestans. The pathogen did not need to overcome diverse resistance mechanisms. It needed to overcome one, and that one vulnerability was shared by virtually every potato plant in the country. A generation ship's agricultural system would face an amplified version of this vulnerability. Crop populations maintained in isolation for centuries would possess far less genetic diversity than even the Irish potato monoculture. Meanwhile, the pathogenic organisms sharing the ship's enclosed environment would be evolving continuously, probing the crop's defenses through the same rapid generational turnover that reshapes all microbial communities. On Earth, plant breeders respond to emerging pathogens by crossing cultivated varieties with wild relatives carrying novel resistance genes. This is the foundation of modern disease resistance breeding. It works because wild relatives exist in natural habitats, carrying allelic diversity accumulated over millions of years of coevolution with pathogens. A generation ship has no wild relatives. It has no natural habitats. When a pathogen evolves the ability to overcome the resistance mechanisms present in the ship's crop population, there is no genetic reservoir from which to breed a resistant replacement. The crew must either find a chemical or biological control method using onboard resources, accept the permanent loss of that crop from their diet, or watch their caloric supply collapse while attempting to scale up alternative food sources that were never designed to bear the full nutritional burden. The loss of even one major staple crop, a wheat variety providing 30% of caloric intake, a soybean cultivar providing the primary protein source, would trigger immediate rationing and long-term nutritional deficiency across the entire population. Micronutrient deficiencies compromise immune function, cognitive performance, and reproductive health. Caloric insufficiency reduces work capacity, meaning fewer labor hours available for the maintenance tasks that keep every other system functioning. Fewer calories means less labor, capacity means fewer repairs, means faster system degradation. Shifting from ecosystem chemistry to human biology introduces a threat that no amount of ecological engineering can fully neutralize. Radiation in interstellar space is not a problem with an engineering solution. It is a problem with engineering mitigations of limited effectiveness. And the residual exposure accumulates in human tissue generation after generation, with consequences that compound across the very timescales a generation ship must endure. Beyond the protective cocoon of a star's heliosphere, the dominant radiation environment consists of galactic cosmic rays, high-energy particles, primarily protons but including heavier nuclei up to iron, accelerated to enormous velocities by supernova shockwaves and other astrophysical processes. The energy spectrum of galactic cosmic rays extends from hundreds of mega-electron volts to beyond 10 to the 20th electron volts per particle. The most biologically damaging component consists of heavy ions, particles carrying high atomic numbers and high kinetic energies, designated HCE particles in radiation biology. When an HCE particle traverses a living cell, it deposits energy along a dense ionization track, shattering molecular bonds along its path. A single ion nucleus at cosmic ray energies can destroy thousands of molecular bonds within a cell nucleus in a single traversal. The resulting DNA damage is qualitatively different from damage caused by lower energy radiation. It involves clustered lesions, multiple simultaneous breaks in both strands of the DNA double helix occurring within a few nanometers of each other. These clustered lesions are far more difficult for cellular repair mechanisms to fix accurately than isolated single-strand breaks, leading to elevated rates of mutation, chromosomal aberration, and cell death. Shielding provides partial protection but cannot eliminate exposure. Low-energy cosmic ray particles are effectively stopped by modest thicknesses of hydrogen-rich materials, such as water or polyethylene. A shield equivalent to approximately 20 grams per square centimeter of polyethylene reduces the dose from low-energy particles substantially. But the highest energy cosmic rays, the HZE particles that cause the most biological damage, are so penetrating that impractical thicknesses of shielding would be required to stop them. Worse, when very high-energy particles strike heavy shielding materials like metals, they produce cascades of secondary particles through nuclear spallation reactions. These secondary particles, including neutrons and lighter nuclear fragments, can actually increase the dose to occupants behind the shield. This phenomenon means that for the most energetic galactic cosmic rays, adding more shielding material can paradoxically make the radiation environment worse rather than better. Optimized shielding designs using hydrogen-rich materials minimize spallation while maximizing stopping power for lower energy particles. But even the best practicable shield configuration reduces the annual dose to perhaps 100 to 200 millisieverts per person, roughly 50 to 100 times the average annual background dose on Earth's surface. Over a 70-year human lifespan, this accumulates to 7 to 14 sieverts of absorbed dose. For reference, a cumulative dose of 1 sievert is associated with approximately a 5% increase in lifetime cancer mortality. At 7 sieverts, the lifetime cancer risk increase exceeds 30%. At 14 sieverts, it approaches levels that significantly compromise life expectancy and quality of life. These doses would affect every person aboard for every generation of the voyage. Children conceived and gestated in this radiation environment face additional risks. Epidemiological studies of populations exposed to elevated radiation, including atomic bomb survivors and populations living in high background radiation regions, document increased rates of developmental abnormalities, intellectual impairment, and childhood cancer at doses comparable to those projected for generation ship inhabitants. fertility itself is vulnerable. Both oocytes and spermatogonia show radiation sensitivity at doses well below those that cause acute radiation sickness. Chronic exposure at the levels expected aboard a shielded interstellar vessel could reduce fertility rates measurably across the population, shrinking each generation slightly relative to the previous one. Radiation-induced mutations interact with population genetics in ways that amplify biological risk across generations. Every cosmic ray that damages a germ cell's DNA has some probability of creating a heritable mutation. Most such mutations are neutral, producing no detectable phenotypic effect. A substantial fraction are deleterious, reducing fitness in ways ranging from subtle metabolic inefficiencies to severe developmental disorders. A very small fraction are lethal, killing the embryo before development completes. Under normal circumstances, in a large population numbering in the millions or billions, deleterious mutations are diluted by the sheer genetic diversity of the breeding population and gradually removed by natural selection over many generations. The mutation load, the cumulative burden of harmful alleles carried by the population, reaches an equilibrium between new mutation input and selective removal. In a small, closed population of several hundred to several thousand individuals, this equilibrium shifts dangerously. New mutations introduced by radiation cannot be diluted by outbreeding with unrelated individuals from outside the group because there is no outside. Deleterious alleles accumulate faster than selection can remove them, a phenomenon geneticists call mutational meltdown. Each generation carries a slightly higher burden of harmful mutations than the one before. Fitness declines incrementally. Fertility drops. Infant mortality rises. Developmental abnormalities become more frequent. The population spirals slowly toward genetic collapse. The minimum viable population question determines whether this spiral can be avoided or merely delayed. Research published in peer-reviewed genetics journals has estimated minimum viable populations for long-duration space missions using computer simulations of allele frequency dynamics over multiple generations. A widely cited 2014 study calculated that under idealized conditions of perfectly random mating, no mate choice preference, no population bottlenecks, and no elevated mutation rate, a founding population of 98 individuals could maintain acceptable genetic diversity over 10 generations. But this calculation assumed conditions that no real human population would meet. Humans do not mate randomly. They exhibit preferences based on proximity, familiarity, social status, and physical appearance. These preferences reduce the effective breeding population size below the census population size, sometimes dramatically. When more realistic social constraints are modeled, the required founding population rises to between 500 and 5,000, depending on assumptions about mating patterns, generation time, acceptable inbreeding coefficients, and whether any active genetic management program is implemented. Even at the higher end of this range, the population remains small enough that genetic drift, the random fluctuation of allele frequencies inherent to finite populations, becomes a powerful evolutionary force. Rare alleles disappear through chance alone. Genetic diversity erodes generation by generation. The population becomes progressively more homogeneous, reducing its capacity to respond to novel pathogens, environmental changes, or physiological challenges. In breeding depression, the reduction in biological fitness that occurs when closely related individuals reproduce compounds the drift problem. In a closed population of even several thousand individuals, consanguinity becomes unavoidable within a handful of generations. The coefficient of inbreeding, a measure of the probability that two alleles at any given genetic locus are identical by descent, rises steadily with each generation in any finite closed population. The rate of increase depends on population size and mating structure, but the direction is always the same, upward. As inbreeding coefficients rise, the probability that an individual is homozygous for deleterious recessive alleles increases. These alleles, normally masked by functional copies inherited from unrelated parents, become expressed. The consequences documented in both human populations and conservation biology programs include reduced fertility, increased susceptibility to infectious disease, elevated rates of congenital abnormality, and decreased lifespan. Over 10 generations, approximately 250 to 300 years, a closed population of 1,000 with imperfect mating management would lose measurable allelic diversity and begin exhibiting detectable inbreeding depression. Over 40 generations, roughly 1,000 years, the genetic consequences could severely compromise population viability. The community might maintain stable numbers for a time through cultural practices that encourage reproduction, but the underlying biological fitness of each successive generation would decline, producing a population that is numerically present but genetically impoverished. Stored genetic material, frozen embryos, or cryopreserved gametes could theoretically inject fresh diversity into the population at intervals. This strategy is used in conservation programs for endangered species and could extend the genetic viability window significantly. But it introduces dependencies on cryogenic storage systems that must function for centuries, on reproductive technologies that require specialized medical equipment and expertise, and on social acceptance of assisted reproduction as a routine practice across generational timescales. Each of these dependencies carries its own failure probability, and each failure probability compounds with every other across the mission duration. Beyond genetics, the sociological challenge of maintaining a functioning human society inside a confined vessel for centuries may represent the least quantifiable but most decisive variable in generation ship viability. No human civilization in recorded history has maintained stable governance, continuous transmission of technical knowledge, and cooperative social cohesion for 1,000 years without significant upheaval. Empires fragment, institutions corrupt, languages drift until mutual intelligibility is lost. Technologies are forgotten when the social structures supporting them dissolve. The history of lost knowledge is not a history of stupidity. It is a history of broken transmission chains. The Western Roman Empire possessed concrete, indoor plumbing, central heating, and a road network spanning a continent. Within 2 centuries of its collapse, the knowledge to construct and maintain these systems had largely vanished from Europe, not because the physics became invalid, but because the social and institutional frameworks that transmitted technical expertise across generations had disintegrated. The recipe for Roman concrete, a material so durable that Roman harbour structures have survived 2,000 years of saltwater immersion, was not recovered until modern materials scientists analysed surviving samples using X-ray diffraction and electron microscopy. The knowledge had not been hidden. It had simply ceased to be taught. Roman concrete is not an isolated case. Greek fire, the incendiary weapon that allowed the Byzantine navy to dominate the eastern Mediterranean for centuries, was lost when the empire contracted and the specialized units responsible for its manufacture disbanded. The exact composition remains debated by historians today. The great libraries and translation academies of the Abbasid Caliphate, centered in Baghdad's House of Wisdom, represented the most concentrated repository of scientific and mathematical knowledge in the medieval world. When the Mongol siege of 1258 destroyed the city, entire branches of scholarship vanished. Not because every last copy of every text was physically destroyed, but because the community of scholars who understood, contextualized, and transmitted that knowledge was dispersed and killed. The texts that survived became artifacts rather than living knowledge, documents that subsequent generations could read but often could not fully comprehend without the interpretive tradition that had once surrounded them. This distinction between documented knowledge and living knowledge is critical for generation ship viability. A vessel could carry a complete digital archive of every technical manual, engineering reference, and scientific paper ever published. It would fill a modest hard drive. But documentation alone does not constitute competence. The ability to diagnose a failing reactor coolant pump requires not just the manual describing the pump's specifications, but the experiential knowledge of what a healthy pump sounds like, what vibration patterns precede specific failure modes, What improvised solutions have worked in past emergencies that were never formally documented, and what subtle environmental cues indicate a developing problem hours or days before instrument readings cross alarm thresholds. This tacit knowledge, the expertise that lives in the hands and instincts of experienced practitioners, cannot be downloaded from a database. It exists only in human nervous systems and transfers only through direct mentorship, through years of an apprentice watching, assisting, and gradually assuming responsibility under the guidance of a master practitioner. A generation ship requires the continuous production of trained engineers, medical practitioners, agricultural scientists, life support technicians, and systems specialists. Each generation must transmit sufficient technical knowledge, both formal and tacit, to its successors to maintain the vessel's complex infrastructure. This transmission requires functional educational institutions, comprehensive technical documentation, practical training facilities, a surplus of experienced mentors willing and able to teach, and a cultural value system that prioritizes technical competence over competing social priorities. A single generation that fails to adequately train its replacements, whether through social upheaval, resource diversion, ideological shift, epidemic loss of senior practitioners, or simple neglect, creates a knowledge gap that may prove irreversible. The psychological pressures of permanent confinement in a limited habitat compound every sociological risk. Research on isolated human groups consistently documents elevated rates of depression, anxiety, interpersonal hostility, and social withdrawal under conditions of prolonged confinement. Studies of Antarctic overwintering crews, submarine deployments, and spaceflight missions show that these effects manifest within months and intensify over time. The longest continuous human spaceflight, Valery Polyakov's 437 days aboard the Mir space station, provided valuable data on individual psychological adaptation, but says nothing about multigenerational psychological sustainability. The crew born aboard a generation ship inhabit an existential condition without precedent in human experience. They did not choose the mission. They cannot leave. They will never see the destination. Their entire lives unfold within a finite enclosed volume under conditions of absolute geographic isolation, performing maintenance on systems they inherited from ancestors they never met, in service of a goal that will be realized only by descendants they will never know. The burden falls heaviest on the middle generations, the people born centuries after departure and centuries before arrival. The founding generation at least carries the memory of Earth, the motivation of a chosen mission, and the psychological anchor of having known an open sky. The arrival generation carries the anticipation of a destination, the prospect of stepping onto a new world and seeing the mission's purpose fulfilled. The middle generations carry neither. They inhabit a vessel they did not choose, travelling through a void that offers nothing to see, maintaining systems whose purpose is to deliver a future they will never experience. Their entire existence is instrumental, a means to an end that lies beyond their lifetimes in both directions. Every civilization that has endured has offered its members some version of meaning rooted in the present, in community, in spiritual practice, in connection to landscape and season and the rhythms of a living world. A generation ship offers a metal corridor, a recycled atmosphere, and a mission statement authored by the dead for the benefit of the unborn. Whether human psychology can sustain purposeful functioning under those conditions for century after century is a question that no experiment has approached and no theory can confidently answer. The psychological pressures of permanent confinement in a limited habitat compound every sociological risk. Research on isolated human groups consistently documents elevated rates of depression, anxiety, interpersonal hostility, and social withdrawal under conditions of prolonged confinement. Studies of Antarctic overwintering crews, submarine deployments, and spaceflight missions show that these effects manifest within months and intensify over time. The longest continuous human spaceflight, Valery Polyakov's 437 days aboard the Mir space station, provided valuable data on individual psychological adaptation, but says nothing about multi-generational psychological sustainability. The crew born aboard a generation ship inhabit an existential condition without precedent in human experience. They did not choose the mission. They cannot leave. They will never see the destination. Their entire lives unfold within a finite enclosed volume under conditions of absolute geographic isolation, performing maintenance on systems they inherited from ancestors they never met, in service of a goal that will be realized only by descendants they will never know. The psychological weight of this condition is unstudied because no analogue exists. Prisons, submarines, and Antarctic stations all offer the prospect of return to open society. A generation ship does not. Social stratification, political conflict, religious schism, and resource disputes have characterized every confined human community in history. Projecting social stability across centuries inside a sealed vessel requires assumptions about human nature that history does not support. Mutinies, coups, civil conflicts, and institutional collapse are not anomalies in the human record. They are recurring patterns that emerge under conditions of resource scarcity, perceived injustice, ideological divergence, and power concentration, all of which a generation ship would experience at some point during a voyage of centuries. The biological and sociological challenges aboard a generation ship are not independent of the engineering challenges described earlier. They interact. A radiation-induced decline in fertility reduces population size, which accelerates genetic drift, which reduces biological fitness, which increases the disease burden on the medical system, which diverts resources and personnel from other maintenance tasks, which reduces the repair rate for degrading mechanical systems, which compromises life support reliability, which stresses the ecosystem, which disrupts food production, which creates resource scarcity, which fuels social conflict, which disrupts educational institutions, which erodes technical competence, which further reduces the repair rate. This cascade does not require any single dramatic trigger. It emerges naturally from the interaction of multiple slow-moving processes, each one individually manageable in isolation, collectively forming a web of mutual reinforcement that tightens with every passing decade. The biological cargo of a generation ship faces the same fundamental adversary as its mechanical systems: time. Ecosystems drift toward instability. Radiation damage accumulates in tissues and genomes. Genetic diversity erodes through drift and inbreeding. Societies evolve in directions that may not preserve the technical competence required for survival. Each process trends toward degradation, and each one accelerates the others. What remains is to calculate what these interacting failure curves mean in aggregate, to ask the quantitative question that determines whether a generation ship is improbable, implausible, or effectively impossible across the timescales that interstellar distances demand. Imagine a chain composed of 1,000 links. Each link is forged from excellent steel by a skilled blacksmith. Each individual link has a 99.9% chance of holding under load in any given year. You would trust your life to any single link without hesitation. Now hang a heavy weight from the entire chain and ask a different question. What is the probability that every link holds simultaneously, year after year for a century? In the first year, the probability that all 1,000 links survive is 0.999 raised to the 1,000th power, approximately 36.8%, not 99.9%, roughly 1 in 3. By the second year, the probability that every link has survived both years drops to approximately 13.5%. By year 5, it falls below 1%. By year 10, the probability that all 1,000 links have survived without a single failure is approximately 0.005%, a number so small it is functionally indistinguishable from impossibility. This is the mathematics of compound failure probability, and it is the single most important concept for evaluating generation ship viability. It does not matter how reliable individual components are. What matters is how many components must function simultaneously and for how long. Systems composed of many individually reliable elements become collectively fragile over extended timescales. This is not a pessimistic interpretation. It is arithmetic. A generation ship is not a chain of 1,000 links. It is a web of tens of thousands of interdependent subsystems, components, biological processes, and social structures, each subject to its own degradation curve, each influencing the failure probability of others. The mathematics governing such a system does not bend towards survival. Over sufficient timescales, it becomes essentially prohibitive without continuous external intervention. And external intervention is precisely what interstellar space does not offer. To make this concrete, consider a simplified but illustrative model. Suppose a generation ship depends on 10 major subsystem categories for mission survival: structural integrity, power generation, atmospheric processing, water recycling, food production, thermal regulation, radiation shielding maintenance, propulsion and navigation, medical capability, and waste processing. Each subsystem encompasses hundreds of individual components, but for modeling purposes, assign each subsystem a probability of adequate function in any given decade. This probability incorporates all internal redundancies, repair capabilities, and component replacement from onboard stocks. Set that per decade reliability at 95% per subsystem. This is deliberately generous. It assumes that within any given 10-year period, each subsystem has only a 5% chance of degrading below acceptable performance, despite all the material fatigue, radiation damage, consumable depletion, and human factors operating against it. 95% per decade sounds almost reassuringly high. The probability that all 10 subsystems function adequately in any given decade is 0.95 raised to the 10th power, approximately 59.9%, a roughly 40% chance of at least one subsystem failing critically within the first 10 years. Over 2 decades, assuming independent failure probabilities for simplicity, the probability of continuous all-system function drops to about 35.8%. Over 50 years, approximately 7.7%. Over 100 years, roughly 0.6%. Over 500 years, the survival probability requires scientific notation and rounds to zero for any practical purpose. These numbers should not be mistaken for precise predictions of any real mission outcome. They are schematic. The actual survival probability of a given generation ship would depend on specific engineering details, redundancy architectures, crew capabilities, and resource inventories that cannot be specified in the abstract. But the qualitative conclusion they illustrate is robust and does not depend on the specific numbers chosen. Even with generous assumptions about individual subsystem reliability, the compound probability of simultaneous multi-system survival declines rapidly with mission duration. The decline is exponential, not linear. Doubling the mission duration does not halve the survival probability. It squares it. The assumption of independence between subsystem failures makes the model optimistic rather than pessimistic. In reality, subsystem failures are strongly correlated. A power generation degradation simultaneously compromises atmospheric processing, water recycling, food production lighting, thermal regulation, and computational systems. A structural breach affects atmospheric composition, radiation shielding, and thermal management in the same instant. These correlations mean that failures cluster rather than distribute evenly across time. When something goes wrong, multiple things go wrong simultaneously, and the crew faces not a single repair task but a cascade of interlocking emergencies drawing on the same finite pool of spare materials, energy reserves, and human expertise. Reliability engineers quantify this clustering through a concept called common cause failure analysis. In nuclear power plant safety assessments, common cause failures, events that simultaneously disable multiple redundant safety systems, dominate the risk profile. A fire in a cable tray can disable both the primary and backup control systems for a reactor cooldown pump. A seismic event can damage multiple independent cooling water intakes simultaneously. The nuclear industry manages these risks through physical separation, diverse design approaches, and defense-in-depth strategies. a generation ship would employ similar strategies, but the duration of exposure to common cause failure initiators exceeds nuclear plant design lifetimes by roughly an order of magnitude for near-star missions and 2 orders of magnitude for more distant targets. The repair rate versus failure rate dynamic introduces a temporal dimension to the compound failure problem that the static probability model does not capture. Early in the mission, repair capability is at its maximum. Spare parts inventories are full. Technicians trained on Earth or by Earth-trained instructors possess comprehensive knowledge of every system. Diagnostic equipment is calibrated and functional. Manufacturing systems, if carried, are operational and supplied with feedstock. During this initial phase, failures are rapidly identified and corrected. Redundancy consumed by failures is restored through repair. The ship operates with comfortable safety margins. As decades pass, this favorable balance shifts. Spare parts inventories deplete. Each repair consumes materials that cannot be replaced. Specialized components that fail beyond the design life of stockpiled spares become permanently unavailable unless they can be fabricated aboard, which requires manufacturing capabilities that themselves degrade. Diagnostic equipment drifts out of calibration. Sensors age, reference standards degrade. The precision of fault detection decreases, meaning incipient failures that would have been caught early in the mission may go unnoticed until they progress to critical stages. The knowledge base supporting repair capability also evolves in potentially unfavorable directions. Technical expertise must be transmitted from each generation to the next through education and apprenticeship. This transmission is never perfectly faithful. Each generation's understanding of the ship's systems is shaped by the experiences of its teachers, the quality of available documentation, and the institutional support for technical training. If social disruptions divert resources from education, if cultural shifts devalue technical work, if key instructors die before transferring critical tacit knowledge, the repair capability of subsequent generations diminishes. A ship that began its voyage with engineers capable of diagnosing and repairing any system aboard might, after 10 or 15 generations, possess technicians who can maintain routine operations but lack the deep understanding needed to address novel failure modes. This gradual erosion of repair capability means that the effective reliability of each subsystem decreases over time, even if the physical components were aging at a constant rate. In reality, physical degradation also accelerates over time as materials accumulate radiation damage, fatigue cycles, and chemical deterioration. The combined effect is a reliability curve that bends downward with increasing steepness, like a ball rolling off the edge of a table slowly at first, then with gathering speed. At some point during the mission, the failure rate curve crosses the repair rate curve. Before this crossing, the ship accumulates safety margin. After the crossing, it consumes safety margin. The crossing point represents a watershed moment in the mission's viability, though it would not be experienced as a dramatic event by the crew. It would manifest as a gradually increasing frequency of minor system anomalies, a slowly growing backlog of deferred maintenance tasks, and an almost imperceptible decline in overall system performance. Temperatures might drift slightly outside optimal ranges. Atmospheric composition might fluctuate more than it used to. Water purity might decline marginally. Crop yields might dip by a few percent. Each of these small deviations is individually manageable. None constitutes a crisis, but collectively, they represent the ship crossing from a state of positive margin accumulation to negative margin consumption. From that point forward, the vessel is living on borrowed time, drawing down reserves of redundancy and capability that cannot be replenished. The duration between the crossover point and eventual system failure depends on how large the initial margins were and how rapidly they are consumed. But the trajectory after crossover is unidirectional. The insidious quality of this process is that the crew living through it would have no clean signal telling them the crossover had occurred. There would be no alarm, no threshold indicator, no bright line separating the era of accumulation from the era of consumption. The maintenance logs would show a gradual increase in repair frequency. The spare parts inventories would show a gradual decrease in stock levels. The environmental monitoring data would show wider fluctuations around set points. But each of these trends would develop slowly enough that the crew on duty at any given time could reasonably interpret them as normal variation rather than systemic decline. The generation that inherits a ship operating at 60% of its original redundancy has no direct memory of the ship at 100%. Their baseline is already degraded. They normalize conditions that the founding crew would have flagged as alarming. This normalization of deviance, a concept identified by sociologist Diane Vaughan in her analysis of the Space Shuttle Challenger disaster, becomes progressively more dangerous as each successive generation recalibrates its expectations downward against a ship that is objectively deteriorating. Can this mathematical trajectory be altered through deliberate design choices? Several strategies have been proposed in the engineering literature, and each offers genuine benefits alongside fundamental limitations. Modular architecture represents perhaps the most practical mitigation strategy. By designing the vessel as a collection of semi-independent habitat modules, each with its own life support capability, power distribution, and atmospheric management, the ship gains the ability to sacrifice failed sections while preserving others. A module that suffers irreparable atmospheric contamination can be sealed off and abandoned. A module whose structural integrity has degraded beyond safe habitation can be depressurized and repurposed as cold storage or raw material reserve. This approach trades habitable volume for longevity, accepting a gradual contraction of the living environment in exchange for continued survival of the remaining population. Modular design genuinely extends the viable mission duration. It transforms what would otherwise be a single catastrophic failure into a series of manageable retreats. But it cannot extend the mission indefinitely because the modules themselves are drawn from a finite inventory. A ship that begins with 20 habitat modules and loses one every 50 years to accumulated degradation runs out of modules in 1,000 years. Long before that point, the remaining modules must support the entire population in progressively more crowded conditions. With reduced agricultural capacity, fewer redundant systems, and diminished manufacturing resources, modularity buys time. It does not buy eternity. Biological adaptation through natural selection offers an intriguing possibility on very long timescales. If a generation ship population is exposed to elevated radiation for dozens of generations, natural selection would favor individuals with more efficient DNA repair mechanisms, greater radiation tolerance, and perhaps reduced sensitivity to the physiological stresses of confined habitation. Over many centuries, the population might evolve measurably improved fitness for the shipboard environment. This process is real but slow. Significant evolutionary adaptation in human populations typically requires hundreds of generations for traits under strong selection pressure. For a generation ship with a 25 to 30 year generation time, 100 generations spans 2,500 to 3,000 years. The selection pressure from radiation exposure would indeed favor radiation-resistant genotypes, but the magnitude of adaptation achievable within mission-relevant timescales is modest. Moreover, natural selection operates through differential reproduction and survival, meaning that radiation-sensitive individuals suffer disproportionate illness, infertility, and mortality. The adaptation comes at a human cost measured in suffering and premature death across many generations, and critically, biological adaptation addresses only the biological failure modes. Human DNA repair mechanisms, however enhanced by selection, cannot fix a corroded coolant pipe or replace a failed bearing. Advanced artificial intelligence and autonomous maintenance systems represent the technological mitigation most frequently invoked in popular discussions of generation ship feasibility, and at first glance, the case for them is compelling. A sufficiently sophisticated AI system could theoretically monitor every component aboard through networks of embedded sensors, predict failures before they occur through pattern recognition in vibration, thermal, and acoustic data, direct robotic repair systems to perform maintenance tasks without human intervention, and compensate for declining human technical expertise by retaining perfect institutional knowledge in digital form indefinitely. If such a system existed and could be made reliable over centuries, it would substantially alter the compound failure calculation by maintaining high repair rates regardless of human factors. The crossover point where failure rates exceed repair rates could be pushed centuries further into the future. The appeal of this solution reflects a broader cultural confidence in computational technology that deserves careful scrutiny. Modern AI systems have demonstrated remarkable capabilities in narrow domains: image recognition, natural language processing, game playing, protein structure prediction. These achievements are real and impressive, but they share a common characteristic that limits their applicability to generation ship maintenance. They operate within well-defined problem spaces using hardware that is maintained by an external civilization. The servers running large language models are housed in data centers with redundant power supplies, climate control, and teams of technicians who replace failed components from a global supply chain. The robots in automated factories operate in controlled environments and are serviced by human engineers using parts manufactured by other factories. Remove the supporting infrastructure, and the systems cease to function, not because the algorithms fail, but because the physical substrate on which they run degrades. A generation ship's AI systems would face exactly this problem. Processors suffer radiation-induced bit flips and gradual degradation of transistor performance as cosmic rays displace atoms in semiconductor lattices. Storage media decay. Solid-state drives experience charge leakage in their floating-gate transistors over timescales of years to decades, even without radiation exposure. Magnetic storage media demagnetize. Optical media degrade under radiation. Sensor inputs drift as transducers age and calibration references shift. Software systems accumulate subtle errors through cosmic ray-induced bit corruption in memory and storage, errors that may not manifest as immediate crashes but as gradually diverging calculations, slightly incorrect sensor interpretations, marginally suboptimal maintenance schedules that compound over decades into significant capability gaps. An AI system tasked with maintaining the ship must itself be maintained, creating a recursive dependency that is easy to state and extraordinarily difficult to resolve. Who maintains the maintainer? If the answer is human technicians, the system inherits every human knowledge transfer vulnerability already discussed. If the answer is redundant AI systems maintaining each other, the compound failure mathematics simply shifts to the AI hardware layer without being eliminated. You have not solved the problem. You have moved it. Furthermore, the kind of general artificial intelligence capable of diagnosing novel failure modes, designing repairs using whatever materials happen to be available, and adapting maintenance strategies to conditions that no programmer anticipated does not currently exist. Narrow AI systems capable of monitoring specific parameters and executing predefined responses are well within current technology. But a generation ship 500 years into its voyage would present failure modes that no training data could have anticipated, combinations of material degradation, ecosystem drift, and social disruption that have never occurred before and will never occur again. Responding to these situations requires not pattern matching against historical data, but genuine creative problem solving, the ability to reason from first principles about novel physical situations using degraded information from aging sensors. Building a mission plan around assumed AI capabilities that have not been demonstrated is the same category of error as building a mission plan around assumed fusion propulsion that has not been achieved. Both represent faith in future breakthroughs dressed in the language of engineering confidence. Cryogenic preservation of a portion of the population has been proposed as a means of reducing the biological burden on the ecosystem while maintaining a genetic reserve. If the majority of the ship's population could be maintained in suspended animation, the active crew needed to operate the vessel would number in the dozens rather than thousands. Food production, water recycling, and atmospheric processing demands would drop by orders of magnitude. The ecological footprint of the mission would shrink to a manageable scale. The concept is appealing in principle and devastating in practice. Cryogenic preservation of whole human organisms is not a demonstrated technology. Current cryopreservation techniques result in lethal ice crystal formation within cells, despite the use of cryoprotectant agents. Vitrification, the process of cooling tissue into a glass-like state without ice formation, has been achieved for small tissue samples and individual organs under laboratory conditions, but has never been demonstrated for an intact human body. Even if vitrification were perfected before the ship's departure, the cryogenic systems, maintaining thousands of vitrified bodies at temperatures below -130 degrees Celsius, would need to function without interruption for the full mission duration. A power failure lasting even hours could allow warming to temperatures where devitrification occurs, killing every preserved individual simultaneously. The cryogenic system thus becomes the single highest consequence failure point aboard the entire vessel, a concentration of risk that contradicts the principle of distributed resilience. The cumulative picture is sobering. Each mitigation strategy offers real but bounded improvement to mission survivability. None eliminates the fundamental constraint imposed by compound failure probability over extreme timescales. Modular design extends the timeline but does not remove the endpoint. Biological adaptation addresses one category of failure at the cost of generations of human suffering. AI maintenance shifts the failure analysis to a different hardware layer without eliminating it. Cryogenic preservation introduces catastrophic single-point failure risks. When these mitigations are incorporated into the compound probability model, they shift the survival curves rightward along the time axis. A mission that might have crossed the failure rate exceeds repair rate threshold at 200 years without mitigations might cross it at 400 years with aggressive modularity and robust AI monitoring. This is a meaningful improvement. It potentially brings near-star missions of 1 to 2 centuries within the realm of the achievable, if barely. But it does not change the fundamental shape of the curve. The exponential decline in survival probability continues. It merely begins from a slightly more favourable starting position. For missions lasting 1 to 2 centuries, targeting the nearest star systems at velocities of 3 to 5% of light speed, the compound probability analysis yields results that fall within a range that might be described as ambitious but not inconceivable. Survival probabilities remain meaningful if not comfortable. The engineering challenges are extreme but grounded in extensions of demonstrated technology. The biological and sociological risks are serious but potentially manageable over such relatively brief spans. A civilization capable of building the vessel would need to accept significant uncertainty about the outcome, but the mission would not be a guaranteed suicide pact. For missions lasting 500 years, the probability landscape darkens substantially. Cumulative material degradation approaches the limits of any known structural material's endurance under combined fatigue, radiation, and erosion loading. Genetic diversity in a closed population has eroded through multiple generations of drift and inbreeding. Ecological stability in a closed biosphere has been tested by centuries of perturbation without external buffering. The manufacturing base aboard has consumed a significant fraction of its consumable reserves. Social and institutional continuity has been tested across roughly 20 generations of confined habitation. Any one of these challenges might be surmountable in isolation. Their simultaneous interaction across 5 centuries produces a risk profile that honest engineering analysis cannot dismiss as manageable. For missions lasting 1,000 years or more, which are required to reach most stars of even moderate scientific interest at achievable velocities, the compound failure mathematics becomes effectively prohibitive. Not impossible in the strict mathematical sense, a non-zero probability remains, but the probability is so small and the uncertainties surrounding it so large that no rational engineering assessment could characterize such a mission as having a reasonable expectation of success. The number of systems that must simultaneously avoid catastrophic degradation, the number of generations that must successfully transmit technical knowledge, the number of ecological cycles that must remain stable, and the number of genetic generations that must maintain viable diversity together produce a survival probability that approaches zero asymptotically with increasing mission duration. This conclusion does not rest on any single dramatic failure mode. It does not require invoking asteroid impacts, equipment explosions, plague outbreaks, or armed mutinies, though any of these could occur. It rests entirely on the quiet, persistent, thermodynamically guaranteed accumulation of small degradations across every system aboard: mechanical, biological, ecological, genetic, and sociological, compounding and interacting over timescales that dwarf the operational lifetime of any system humanity has ever built or maintained. The barrier to interstellar colonization via generation ship is therefore not primarily a barrier of speed, though speed matters enormously because faster transit reduces the duration of exposure to cumulative risk. It is not primarily a barrier of energy, though the energy requirements for accelerating a habitable vessel to interstellar velocities are staggering. It is not primarily a barrier of distance, though the distances are immense beyond human intuition. The primary barrier is time. Time is the medium through which entropy operates. Every second that passes allows another atomic displacement in an irradiated hull plate, another stress cycle on a rotating structural member, another fractional degradation of a polymer seal, another metabolic cycle in a microorganism that is slowly shifting atmospheric chemistry in an unfavorable direction, another meiotic division in a human germ cell, carrying a slightly higher mutational burden than its parent, another year of institutional memory becoming slightly less precise, slightly less comprehensive, slightly less capable of maintaining the systems that keep everyone alive. None of these processes is dramatic. None would make a compelling scene in a film. They are invisible, incremental, and relentless. They do not care about human determination, ingenuity, or courage. They are consequences of physical law, operating at scales from the atomic to the societal, and they share a single common property. They all trend in the direction of degradation, and none of them spontaneously reverses. The second law of thermodynamics states that the entropy of an isolated system never decreases over time. A generation ship is the most isolated system imaginable. It exchanges no material with its environment. Its energy inputs are limited to whatever power systems it carries. Every ordered structure aboard, from the crystalline lattice of a turbine blade to the helical strands of a crew member's DNA, exists in a state of thermodynamic improbability that is maintained only through continuous expenditure of energy and effort. The moment that expenditure falters for any reason, in any subsystem, disorder advances. This does not mean generation ships are physically impossible. Physics does not contain a theorem prohibiting them. It means that their feasibility is a function of mission duration, and that function is steeply unfavorable. Short missions to nearby stars sit at the outer edge of plausible ambition. Medium-duration missions face compounding risks that may exceed recoverable thresholds. Long-duration missions encounter a statistical landscape that is essentially indistinguishable from impossibility given any currently conceivable technology. The honest assessment is not that humanity cannot reach the stars. It is that humanity cannot reach the stars slowly. The generation ship concept attempts to substitute endurance for velocity, to trade speed for patience. But the universe prices patience in entropy, and the cost increases exponentially with every century of transit. The stars are not hidden behind a wall of distance alone. They are hidden behind a wall of time, and time is the one barrier that engineering cannot dismantle, only race against. If interstellar travel is ever achieved, it will almost certainly require velocities far higher than current propulsion concepts can deliver. Velocities sufficient to compress transit times from millennia to decades, reducing the exposure window through which entropy, radiation, genetic drift, ecological instability, and social decay can erode a mission's viability. The generation ship, as a concept, is a monument to human ambition confronting the limits of physical law. It deserves admiration for the scale of its aspiration and honesty about the mathematics that constrains it. The universe is not hostile to life, it is indifferent. And indifference, sustained across centuries in the cold vacuum between stars, is far more dangerous than hostility. Hostility can be fought. Indifference simply waits, patient and absolute, while entropy does its work,